Okay. Hi guys, thank you everyone for coming out. My name is Tyler Pai and my partner is Joseph Baki. Today we're going to be presenting on our capstone entitled Charge Tracing for Determining Electrical Facility Effects on Electric Spacecraft Propulsion Systems. Can you go to the next slide, please?
I was presenting the video. Was it still not working?
Yeah, it's still not working. That was Tyler actually talking.
Oh, that was me talking, yeah.
Yeah.
Yeah, can you bring up the actual presentation and then just go through the slides?
It's playing the sound too, so you have to pause that. Okay. You want me to start over or?
Just share. I'll share the presentation, Joey.
Yeah, let Tyler share the presentation then.
Okay.
So I can't see you guys' screen. Can you guys see the presentation?
Yeah, we can go and put it on view the slideshow from beginning. Yeah, there you go.
Hi, everyone. It's great to see so many faces virtually up. Can you guys
we can actually hear it now.
Okay. I will restart. From beginning. Hi, everyone. It's great to see so many faces virtually out there today to come and watch this presentation. My name is Tyler Bai, and my partner is Joseph Baki. Today, we're going to be presenting our capstone, which is entitled Charge Tracing for Determining Electrical Facility Effects on Electric Spacecraft Propulsion Systems. And without further ado, let's get started. The majority of this project is going to be spent talking on the confinement cage we designed. However, the confinement cage we designed was for the furthering and testing of the Hall effect thruster within the policy lab. So I did want to go into some background on Hall effect thrusters. The components of a Hall effect thruster are cathode, anode, electromagnet, backplate, and channel. The anode is where the plasma is going to be generated within the Hall effect thruster, and then the electromagnets concentrate the thrust plume within the channel. The thrust itself from the plasma is generated through the ionization of the xenon gas, and while there are other gases you could choose to use, for a Hall effect thruster, xenon is chosen because of its relatively high mass among other inert gases. The Hall effect thruster is an electric propulsion system that's used on mission in space, and while it does operate within space, the testing for the Hall effect thruster happens within a vacuum chamber on Earth. Within the testing on Earth, there is a divergence in results from what would be expected to happen in space. Some of this divergence is known, and some of it's unknown. Some of the known divergence is the ion interaction. In space, the ion interaction is much stronger, and this holds the electrons to the thrust axis, whereas on Earth, the ion interaction isn't as strong, so the electrons are not going to be held as closely to the thrust axis. On Earth, the ambient pressure is going to be higher than that in space, and the plasma plume density is also going to be higher on Earth than that in space. This is going to open up new conduction pathways within the vacuum chamber that wouldn't have existed within space, viewing the results. The goal of the confinement cage is to eliminate some of these known anomalies within the chamber, specifically electric anomalies like current leakage and induced magnetic or electric fields.
The constraints of the design relating to the dimensioning and overall size of the design of the project refer to the image to the right. This is the large vacuum chamber available in the ALPE lab. The chamber has a length of 68.19 inches and an inner diameter of 41 inches. The square support has a cross-section with a length of 30.97 inches. The overall design must fit within the length and diameter of the chamber for optimal testing. It should slide and fit within the 80-20 strut railing, providing support for the design. Using the only design available at this time provided by AFRL, a smaller design is created for smaller testing by universities with less allocation and funding for vacuum chambers. The design must also be large enough to fit the Western Hall thruster currently being used for research purposes and other thrusters currently being designed by students in the lab. Currently, only Hall effect thrusters have been tested in this type of apparatus, but hopefully in the near future, electron cyclotron resonance thrusters and more can have the opportunity to further research on electron discharge in ground vacuum chambers. Due to the design constraints listed above, the design must fit within the large vacuum chamber located in the ALPE on-campus laboratory. The decision was to change the 6-ring design, formerly used by AFRL, into a 2-ring design. Ring 1 would be 26 inches in length with a hexagonal design, and the hexagonal design would have a 6-strut pieces measuring 30.31 inches at its widest point and 27 inches in height. These dimensions stand true for the 2-ring design, with the only difference being the length of 36 inches. The strut chosen was 80/20 strut with 1 inch by 1 inch square T-slot design. We chose this material due to an abundance of it available within the ALPE. As you can see from the image to the right is a Honeycomb corrosion-resistant 3000 series aluminum honeycomb core mesh. The Honeycomb Mesh was purchased from McMaster Carr and is identical to the mesh used by AFRL in their design, the part number 9635K4. To make the device as close to the original as possible, parts that could be identical were kept as such. Cell size is 1/2 inches in size and 3/4 inches in thickness. Each piece was cut to fit within the 80/20 strut square openings differing for each ring. Although the mesh will not support any load besides its own in weight, it can hold a maximum capacity of 165 pounds per square inch. Now, onto the more finer mesh used. This is stainless steel wire cloth. It has an opening size of 0.02 inches with a wire diameter of 0.013 inches. Open area is about 37%. It's the same mesh product used by AFRL and was also purchased from McMaster Carr's website. The mesh is cut to specification to cover the entire inside of the confinement cage. The only separation between the fine meshes are where ring 1 and ring 2 meet, where the insulation is, and where ring 2 and the beam dump meet, also where insulation is. On to the next design aspect, the back wall. The back wall is the location where the preferred thruster will be attached and tested. 2 vertical strut beams can be adjusted for the optimal placement of the thruster in the horizontal direction, and on the vertical beams, a back plate will be mounted for the adjustment in the vertical direction. The back wall is technically a connection to the first ring in terms of circuitry. Theoretically, no charged particles should escape and go towards the back wall, but there are mesh inserts in case this does occur. Like I said before, the back wall is a part of the first ring. The first ring is the shorter of the 2 rings. It is shorter because that is where the charged particles are all coming out of the thruster. On the opposite direction of the back wall is the beam dump. The beam dump is where the thruster plume of escaping ionized xenon particles and free electrons are moving to. The angled hexagonal shape is to prevent particles from refracting off the wall and going back to the direction of the thruster exit. The angle of the beam dump is approximately 10 degrees into the apparatus. It is made of the same mesh materials as the 2-ring assembly, as well as using the same 80/20 strut as the frame of the system. The hexagonal hole left in the beam dump is covered with an acrylic transparent material that a camera lens can fit into for testing purposes on the thruster. Next is the ring separation insulator. The ring separation insulator is designed identical to the dimensions of the outside hexagonal dimensions of the ring. Each insulator is identical to the other for manufacturing purposes and construction simplicity. The insulation ring is designed as 6 separate rectangular members that cover each ring end completely to avoid current leakage between separate partitions. D10 fiberglass material selection provides ample insulation between the rings and avoids any gaps to prevent leakage from escaping charged particles from the cage system. These ring separation insulators are found between rings 1 and 2 and between ring 2 and the beam dome.
The experiment was conducted within functional multiphysics. We chose to use a 2-dimensional cross-section instead of a 3-dimensional design because of the symmetry of the confinement cage design. One difference that does need to be noted for a 3-dimensional model is that there would be space surrounding the Hall effect thruster. While this is ignored in the 2-dimensional model, the space surrounding the Hall effect thruster would have low conductance, which would be in the favor of the confinement cage simulation. Within the simulation, we used electrostatics and electric current toolboxes. There were ground locations applied at the beam domes and backfall, which are the left and right edges of the 2-dimensional model. A test voltage was applied at 250 volts. This information was taken from a 2016 senior design group that had designed a Hall effect thruster for the Ulti-Lab. The first simulation that we ran was the electric potential across the cross-section. And while the simulation isn't dealing with one of the parameters we're trying to meet, it does give validation in the design. This simulation was used more to validate the 2-dimensional cross-section design. Within the 2-dimensional cross-section, you'll see the potential ranges from 0 volts at the ground to 250 volts near the Hall thruster. There's no potential spikes in unforeseen locations, which is a good thing within this simulation, no random electrical effect. But you'll notice that the potential drops as you move away from the thruster. This would be expected. In an ion stream, there's going to be positive and negative ions, and as they collide with each other, they should start to neutralize each other. This would cause a potential drop within the ion stream as time elapses throughout the experiment. The second simulation that we chose to run within console is the electric current distribution, and this is one of the key parameters that we were trying to make our confinement cage meet, which is minimal current leakage. The current density within the confinement cage ranges from 10 to the negative 17 to 10 to the negative 7 amps per meter squared. Amps per meter squared within itself is a very large unit, and then you have to take into consideration that the cross-section areas are in square inches, which is going to give a low current at any point within the cross-section. For a reference, 1 square inch is 0.0006 square meters, so you can really even multiply those current densities by 10 to the negative third for what the current is going to be. This minimal current is going to allow for minimal current leakage throughout the cross-section. The third and final simulation that we chose to run within console is the electric field distribution. And the electric and magnetic field distributions really are the second key parameter that we're trying to meet with our confinement case. On Earth, there's already electric and magnetic fields on the surface, and this is going to affect experiments within the vacuum chamber. Within our simulation, we found that the electric fields range from 10 to the negative 24th to 10 to the negative 4th volts per meter. And then when you take into consideration that the section dimensions are in inches, and 1 inch equals 0.0254 meters, the effect along the electric field line is very minimal. Within space, there's not going to be the random electric and magnetic fields that we see on Earth. And the simulation validates the confinement cage design by the minimal electric field induced within the confinement cage cross-section. There were a couple of parameters that had to be met before we could actually give this design the go-ahead to be built next year. The first parameter, and probably most practical of all the parameters, is that the confinement gauge has to fit within the vacuum chamber. On top of that, there were a couple of electrical parameters we needed to meet, mainly low current leakage and minimal electric fields or minimal magnetic fields. The confinement gauge has been shown to fit within the chamber. We were able to get a copy of the SolidWorks for the vacuum chamber in the ALPE lab. And then after constructing the data assembly, you can see within our paper that the confinement gauge does fit within the chamber. In terms of electrical parameters, those weren't met as previously mentioned in the simulation. And because the sign works in the simulation, it validates the confinement gauge. While we have during the semester working on this design, there's always room for improvements within our design. The one thing that we thought could probably have been done better was the multiphysics simulation. The multiphysics simulation software was a new program to both of us, and we only had a semester work with it, so it wasn't the most refined simulation. One thing to consider is that there are themes within the vacuum chamber touching the confinement gauge. Would this affect the confinement gauge circuits and give different results? That would be something that would need to be looked into before the confinement gauge was run to make sure that there wasn't a lot of current leakage into the vacuum chamber. The console license at Western also doesn't have particle tracing. Particle tracing was something we wanted to do, but because Western did not have the particle tracing, we couldn't do that within our experiment. And then, as mentioned before, the two-dimensional model is missing much of the space inside the cage, and the conductance of that space would be much less than the conductance of aluminum or steel, which would change the results within the simulation. The largest constraint that we had during this project was that the project was conducted entirely during the midst of COVID-19. As everyone knows, everything takes place as long when you're working remotely. We had limited access to the lab in the university, which meant that we spent extra time waiting for email correspondences from people within the lab for parameters on things such as controllers or the dimensions of the vacuum chamber. Another problem we came across was remote login. There were a lot of computer malfunctions and crashes, so things that would have went quicker within person at the university ended up having to be redone because the program would crash quickly and there wouldn't be a file saved, and then you have to remote log back in, and that takes quite a bit of time to do. Before Joe and I open up the field for questions, there are a lot of thank yous that need to go out for this project. There were so many people that helped with this project in ways that it wouldn't have been possible to do the project without them. Dr. Lemmer, our faculty advisor, who answered so many urgent emails concerning design, reaching out to businesses trying to order parts for the confinement gauge, trying to get pieces to work with other pieces that weren't made from the same company, and learning how to do that, and her just teaching us how to interact in the design side of industry. Mike Holmes and Nicole Simmons are industry mentors who answered so many questions about the confinement cage and gave us research that they had from their confinement cage that better helped us to design our confinement cage. The Lee Honors College was a financial sponsor for this project, and without them, we wouldn't have had the budget to order many of the parts. Dr. Fresta, our senior design 2 professor, who gave us so much advice in class on just how to move forward with the senior design project and what that actually entails. Christine Thomas, the administrative assistant and scholarship award liaison, who ordered so many parts for this project, which we wouldn't have those parts if she hadn't ordered them. Christopher Boucher, console multiphysics tutorials creator. Without those multiphysics tutorials, the simulation wouldn't have been able to be done. And then the many students in the ALPE lab who responded to emails concerning controller parameters and vacuum chamber information. Due to COVID, it wasn't always possible to get within the lab and get those information. So it really was appreciated that you guys responded back to us and gave us the parameters for the equipment within the lab. Attached here are the references that was used for the information in this presentation that we would not have been able to know by ourselves. But if you want to look more at those, I can send you the paper if you email me. Like I said at the start, it's just so great to see so many faces out there watching. It looks like we have about 6 minutes left in the presentation time. So
Okay, guys.
well, if you guys have any questions.
Okay, guys, thank you for the presentation. Now, of course, presentation is open to the questions. Please ask your questions unmuting your mic, or you can also type your question in the chat room. Question and comment, of course. So meantime, I have a question, guys, for both of you. What is the most challenging part, and what is the new thing you learned from this project?
Sorry, could you repeat that? I didn't quite hear what you said at the beginning.
So what is the most, let's say, challenging part was in this project, and what is the new things you learned from this project?
I think first off, the most challenging part about this project was the COVID restrictions. There were only so many people allowed in the lab every day and every session. And they all worked with us great. And my favorite part, the most rewarding part, was the plasma knowledge and physics knowledge I gained from this, because I'm a mechanical engineering major. I don't have a lot of background in that, but with the ALPE lab, they've all been super forward with helping me, and it's very excited for me to learn it. So thank you to all those people.
Okay.
I think for me, the most challenging part was learning how to work within COMSOL. Before the project was proposed, I'd never actually heard of the program, and just learning how to use that and actually get a simulation on top of multiple simulations up and running in time for the presentation.
Okay, guys, thank you very much. So anybody has any questions to our presenter, please? Go ahead.
I have a quick question. First, Tyler, I feel you on COMSOL. That's quite a hard pill to swallow, doing that over a single project timeline. COMSOL is an animal, especially on the latter half. You know, designing a model is fine, but then you have to communicate that model to somebody else, and that's just that's a huge learning curve. I feel you. So the structure itself, does it have any provisions for instrumentation at a future date?
Yes, so, there needs to be electrical circuitry attached to each ring because they're separate circuits. Neither of us are electrical majors, so we didn't want to mess with that, but hopefully someone in the near future could pick that up as maybe a senior project, or someone in the lab can work on that.
I mean, that's what grad school's for, right? Right.
Any other question, guys?
Yeah, I have a question. So you couldn't get a particle tracing model, but can you talk to say an ion is coming out of the thruster with 250 volts of energy in some direction in the cage? Can you describe what the path of that ion should roughly look like, and what happens when it gets to the wall? To the cage wall, I mean?
Yeah. 150 volts energy.
So the ions are coming out. I don't want to use the same analogy I was given, but they're much more massive than the electrons coming out at the same time. And hopefully they will neutralize since there's no ground in space. But they will be coming out and crashing into those electrons and crashing into the walls. That is why we made the beam dump 10 degrees, so they don't reflect off of that beam dump and back at the thruster. I'm not sure if that fully answers your question.
do the ions change direction at all in their path?
Not too
Compared
much.
to the other, yeah, compared to the electrons, I meant. Yeah.
Yeah,
Yeah,
that's
that's a good answer. That's a good answer.
Yeah, they're not going to change as much as the electrons. If you think of like the energy like mass, they're going to have a lot more mass, so it's kind of a momentum type thing. The more momentum you have, the harder it's going to be to change your direction.
Okay, guys, thank you very much. So we are now in this presentation here. Once again, thank you very much. The next presentation is just starts in 3 minutes, guys, or 2 minutes.